So welcome everybody. Today we have Gernot Akemann from Bielefeld University, and he will be talking about non-Hermitian random matrices with complex eigenvalues, and he will answer the question on how to characterize their local statistics. So Gernot, whenever you're ready, please go ahead.
We can go, yes. Thank you, Andreas, for the very kind introduction and invitation. I will not fully answer this question, how to characterize the local statistics, but at least I will give some hints and say what questions remain to be answered, many of them actually. So what I report upon is mainly two joint papers with my students and former students. Can you see my mouse somehow or not really?
No, it's stuck.
It's stuck?
Yes.
Oh.
We can see a hand, but it's not moving.
Okay, so I cannot even use that, but that's okay. I will manage. So the first paper with Adam and Patricia is about spacings in real eigenvalue statistics, but this gives also some interesting clues about how much you can expect to learn from spacing statistics in general. And the second paper, the second paper is about real eigenvalue spacings, and the first paper is about complex eigenvalue spacings. You will see. I will first review some results about random matrices in general. I do not expect that you are an expert, so of course I will have to keep things simple. So first of all, I will talk about random matrices, Hermitian or non-Hermitian. I will define what I mean by that. I will say a little bit about symmetry classification, and then of course about eigenvalues, as the title suggests. I will then have to introduce determinantal point processes, or for short DPP. So if you forget this acronym, this will appear, hopefully not many more. And once we have this set up, we can talk about large n limits, universality, and kernels, and so on. Now, the new part that comes will be about spacing distributions, both between real eigenvalues, so between consecutive real eigenvalues, or eigenvalues in the complex planes, and there I mean the spacing in radial distance. And this will include some discussion on symmetry classes, including general beta. Okay, before I conclude. So,
sorry, Gernot.
Yes.
Sorry, just are you moving the slides or not yet?
Yes. Can you not see it?
No.
No.
Okay, let me stop share and start again. I'm sorry for this. Can you see it now?
Now we are seeing several slides, yes, different slides.
Good. So this slide has the title Classical Gaussian Random Matrices, okay?
Yes, yes.
Good. So whenever there's a problem, please interrupt. And of course, if you have a question, also do interrupt. So we're talking about n times n matrices here. And
we can also see your mouse now. You can use it.
Excellent. So they are either Hermitian or they are non-Hermitian. They have a Gaussian distribution. So how does this come about? You take probability distribution properly normalized, of course, where you have e to the minus trace h square. And if you write that in summation convention, you see this simply means that you have independent Gaussian random variables, where in the Hermitian case, of course, bear in mind that the upper triangle and the lower triangle are related. And that means that the diagonal parts, which are real, and the off diagonal have different variances. Now, if you take just non-Hermitian matrices, then this is not the case. So then really all matrix elements are independent Gaussian random variables. Okay, so now we talk about eigenvalues. So again, for the Hermitian case, this is simple. So you all know from linear algebra that you can diagonalize a complex Hermitian, real symmetric, or self-dual quaternion matrix using an orthogonal transformation, unitary, or respectively symplectic transformation. And the matrix here in the middle is the diagonal matrix of real eigenvalues. And the name of these three ensembles are Gaussian orthogonal ensembles, so GOE, GUE, and there's an S missing here, GSE. Okay, so I think for Hermitian, this is not so surprising. Now for complex, for non-Hermitian, let's, for simplicity, take complex non-Hermitian. The best you can do is what is called a Schur decomposition. If you want to use a unitary conjugation, so you can bring it to upper triangular, or if you wish, lower triangular form. So, and on the diagonal, you get the complex eigenvalues, and on the upper triangle, you get complex Gaussian random variables. And then you plug that in the trace here, and then at the end, of course, you will want to know something about the joint density of complex eigenvalues. If you do that for quaternions, you can use the 2n times 2n dimensional complex representation. You can also diagonalize, and then you get complex conjugate eigenvalue pairs. And if you take real non-symmetric ones, the best you can do is you can get blocks of, so it's 2 by 2 block diagonal. And in these blocks, you have also either complex conjugate eigenvalues or real eigenvalues. And I will not tell you how the distribution is in general, just these ensembles were introduced by Jean Genibre, whom I should have mentioned here. And now we often call them parallel to the classical ensembles GOE Genibre, so Gin OE, Gin UE, Gin SE. So these are the labels I will give. And notably, the one with orthogonal symmetry has been the most complicated. That has taken, I think, 40 years before the spectral statistic was understood. And the reason is that there may be real eigenvalues. This is very simple to understand. If you have a real matrix and you take the characteristic equation, this is a real equation. So if you solve this characteristic polynomial, this will have complex conjugate solutions or real solutions. So for example, when the dimension is odd, there will always be at least one real solution. Okay, so these are the matrices we want to study. Now, what are the questions I would like to address? So first of all, I would like to look at the joint distribution of eigenvalues and then study the spectral statistics. This we can do to full extent for Hermitian, as I will briefly remind you, and to a lesser extent for the complex non-Hermitian. And another question you may want to ask, of course, is, are there more than these classes? These are the classical ensembles. So the Hermitian ones are called Wigner-Dyson or WD. They go back to the 50s and 60s. And the ones from Genibre are not much younger. And we will see that, yes, indeed there are, and I will try to explain a little bit how many and why. Now, as a remark, I will not consider in this talk random matrices that are not compactly supported for finite n. So let me give an example. If you take a unitary matrix distributed with respect to harm measure, then clearly its eigenvalues will be phases, and they live on the unit circle. So this is for me as good as Hermitian because they are on one-dimensional manifold. So these will not be considered, although some of the spectral statistics is very similar. They were introduced, in fact, because they are simpler in some extent. And also in the non-Hermitian case, suppose you take a unitary matrix, a big one, and then you start removing rows and columns. So you get a sub-unitary matrix. These are called truncated. And clearly here, the eigenvalues that were previously on the unit circle, they will start move in. So this will live then on the inside the unit disk. And this is also something that is currently much studied, but I will not talk about these. So just to clarify. Okay. So
are PT symmetric matrices, are they a class in itself, or?
Well, that's a good question, but you see, I will only talk about matrices that have complex eigenvalues generically. So I will not talk about matrices that are non-Hermitian but have a real spectrum. Mm-hmm. In one of the cases, you can fine-tune them to behave in this way. The real Genibre ones, if you consider not a rotational invariant spectrum, but very close to the real axis, if you don't put enough energy, you cannot create complex conjugate pairs. So, but this is really a special case. So if I say non-Hermitian, I really mean generically they have complex eigenvalues. Okay, good. So, of course, we first look at Hermitian ones. So there are 3 plus 3 plus 4, so 10. And the names related to that are Wigner Dyson for the first 3 that were the ones already introduced. Here, the reason was that, as I will also show in a picture, people introduce these random matrices to study quantum mechanical Hamiltonians that have some degree of chaoticity. And these 3 classes you can think about as Hamiltonians that have time reversal invariance. So these are called C. That will allow you, when the spin is even, so integer, to choose your Hamiltonian in a real basis. So then you are in the GOE case, and the other two have also interpretations. The second set of 3 were introduced by Jacques Weber-Ascott. They are called chiral because they have this chiral structure here that I tried to sketch. So if you come from field theory, you will see that these anti-commute with gamma 5, so they have a chirality. And it turns out that on the physics side, they are related to gauge theories where you want to study chiral symmetry breaking. And there's a very nice paper by Peskin who shows that there are, depending on the representation of the gauge group, 3 different chiral symmetry breaking patterns. And those will be the ones that appear here if you think about this as sigma models. Then there are 4 further ensembles. So I just give one example. So these are antisymmetric Hermitian. So I times an antisymmetric matrix, but there are 3 others. These were studied by Altland and Zirnbauer, and they also gave a unifying picture in terms of symmetric spaces. They introduced this Cartan classification, so they typically label their random matrices with A, B, C, D. Now, in all these 10 classes, we fully understand the spectral statistics, and we also know that they are universal, so they hold also going beyond Gaussian distributions. I will talk a bit about this. So what about non-Hermitian? So 3 we have already learned. These are the 3 Geneva ensembles. Again, there are 3 chiral versions that are also studied. I did some work on this with my students and co-workers, but most of all, James Osborne is to mention here, who first wrote down this model correctly and its solution. So if you remember, we had this operation C and P, and in a very important paper, Denis Bernard and André Leclerc introduced 2 further operations, Q and K. So all of these are unitary conjugations. And they made a classification of Dirac operators, actually. And this applies also to complex non-Hermitian random matrices. Now, initially, if you look at the archive, there were not 38 classes, but 43, I believe. And then there was a more recent paper by the group of Ueda et al., also Kawabata. They revisited this classification and found that there had been some mismatch. So Bernard and Leclerc reacted and have updated their archive paper in a version 2. So the classification is valid with some small corrections. Now, there's also a relation to symmetric spaces by Ulrika Manier. Now, the thing is that only in these first 6, so Ginevra and chiral, we have fully understood the spectral statistics. And the question is, of course, what about all the others? Do we know something about the universality class and so on? And let me say here, I will distinguish the word symmetry class. So that's clear, that's a matrix that has a certain symmetry, like transposition or so, and universality class. So what is universality class? Is a class of eigenvalue correlations, and I hope this will become a bit clearer in a moment. Okay, so any questions at the moment about symmetry classes? This was very brief, but
may I ask one?
Sure.
Yes. I'm not quite sure about the dimensionality yet. Each matrix is n-dimensional, but how many matrices are there?
Okay, so in the chiral case, it's actually, this is a good question. This is actually 2 matrix models. So there's a matrix W1, n by n, and W2. We can also choose them to be rectangular, then we get some 0 modes. This is also important, but this is the dimensionality. And if you think about it, the Geneva ensemble it has a Hermitian part and an anti-Hermitian part. So it's also, if you start from Hermitian matrices, a 2x2 matrix model, a 2-matrix model.
Do you ever consider an infinite number of matrices?
We have studied products of random matrices. This would be an entirely different talk. So we can also solve products of Genero matrices completely at finite matrix size and a finite number of products. This is a determinantal point process. If you're interested, I can give you some references at the end.
I was just looking for the analog of statistical mechanics. You started off with the partition function.
Yes.
An infinite dimensional quantity.
So the matrices I will talk about here in this talk will be basically zero-dimensional quantum mechanics. So there's no people have done it very early on. I think this famous paper by Brezin, Itzkin, Zuber, and has one-dimensional quantum mechanics. So, but I will not talk about this.
Thank you.
Maybe I ask the same question as Philip. The number of dimensions doesn't determine the number of classes, no? So
No.
the 38 classes exist anyway, which dimension of matrix you have, no?
Yes, so we talk about finite dimensional n by n matrices. Okay, this J maybe is 2n by 2n, but I mean, that's good enough, no? So, okay. Good, so now let's go to eigenvalues. So it's clear that if you make a transformation, this introduces a Jacobian, and the Jacobian here in most cases will be the Vandermonde determinant. So that's just the difference of real lambda I minus lambda j. And you can also write that as a determinant of lambda I to the power j minus 1. Now, remember we had 10 classes here. So these are the 10 symmetry classes of Hermitian random matrices. Now it turns out that you can write them as two classes of joint densities. So JPDF is joint probability distribution functions of real eigenvalues. And this is something that's in a very nice paper by Ivanov, who pointed out that, the symmetry classes and symmetric spaces are one thing, but if you want to go down and calculate spectra, you need to go to the spaces, and they all look very similar. And there's a nice paper also by Mario Kieburg and my former students, Tim Würfel, who made this list. So the three classical ones, so GOUSE, they look like this. So you have a Vandermonde to the power beta. Beta is 1, 2, or 4. 1 for orthogonal or real matrices, 2 for complex, 4 for quaternion. And you have this Gaussian factor here. That's clear. That comes from the trace of H square. And the other 6 take this form. So you have, again, a Vandermonde, but of squared variables. You have a Gaussian, and you have this extra factor here. So this comes from choosing, for example, rectangular matrices or from this particle hole symmetry. And all you have to remember that this alpha labels here the number of zero modes, and in some classes there can be a finite arbitrary number, and in other classes, like in these 4 classes, there will be only 0, 1, or 2. Now the upshot is that all these 10 ensembles or 2 classes of JPDFs form determinantal point processes or Pfaffian point processes. I will explain on the next slide what that means. But just to bear in mind, you have some function that determines all correlation functions. That's called the kernel. And for all 10 ensembles, this is given in terms of Hermite polynomials or Laguerre polynomials. Okay, so everything is very explicit for finite matrix size and very clearly determined. So here's an hopefully it was hopefully more readable slide that I could recycle. So let's look at beta equals 2. So Vandermonde to the power 2. These all ensembles that have this are determinantal point processes. So what does that mean? It means that the joint density can be written as a determinant of some function of 2 variables that is called kernel. And that is constituted of a set of polynomials here that are orthogonal with respect to this weight function. So either this Laguerre weight or Gauss weight. And the correlation functions, so for example, the density, 2-point function, and so on, how are they obtained? They are obtained by integrating out all but k of these eigenvalues. So if you take the density, you integrate all but 1, and you get the kernel. And in general, these RK, these k-point correlation functions, are given by the determinant of the same kernel. or if I put here k equal n, we get n factorial times the joint density. So a distribution of points with this, that satisfies this is called determinantal point process. Now, eventually, when we want to say something about universality, we will take the dimension of matrices to become large. Now, if you look at this expression here, you note the only thing that depends on n is this kernel here. I will give two examples, but the determinant size here for the k-point function, so 1 for density, 2 by 2 matrix for 2-point function is finite. So all we have to analyze is the large and limit of this object here. And this is a huge simplification. Now, I could write down the same thing for replacing that with a Pfaffian. You can think of the Pfaffian of an antisymmetric matrix, and you square it, you get the determinant of that matrix, but I will not give more explicit formulas than that. Okay, so we are now from matrices to eigenvalues to point processes. So how do we analyze the statistics? So before we do that, let me give two examples. One is the GUE, so Vandermonde square, and the kernel is just the sum over orthonormal Hermite polynomials and these Gaussian weights here. The second example is the Geneva ensemble, and I think I did not write the joint density. So the joint density is again Vandermonde modulo square times the product of e to the minus z modulo square j. And here the kernel looks like this, and you get power. So it's very simple, and you can see also the large and limit. Well, this will just become an exponential. So it's a very simple thing. Now, I mind you here that for the non-Hermitian ensembles, it is not true that the joint density is a Vandermonde to some power beta. That is only true for Hermitian ensembles. So the statistical mechanics interpretation for Hermitian ensembles is simpler because you can raise the Vandermonde to the exponent, then you have a logarithmic interaction, and you know what this is statistically mechanically. For these ensembles, this is not so clear. So now, for the non-Hermitian ensembles, only for the first 6, we know that these are determinantal or Pfaffian point processes, and for the others, we don't know what the eigenvalue distribution is. But we will know something, and that's what will come later. Okay, so here comes a slide summarizing a lot of results for Hermitian random matrices, so for real eigenvalues. I hope it's okay if I jump back and forth, but okay, so let's see what is plotted here. So first of all, you have to distinguish between global statistics and local statistics. So what do I mean? Global statistics is you take, let's say, the density. So you take this kernel here at equal arguments, you let n go to infinity, and you look at the distance of points that are of order 1, let's say. What you find is that in all 10 ensembles, you find this Wigner semicircle, and that's in fact true for all real beta. So even if you take a Vandermonde to power real beta, this will give a semicircle. So that means if you rescale your eigenvalues, this will be compactly supported. And there will be different behavior locally. So when you zoom in, you take a magnifying glass and you zoom in here, what this is called bulk, or you zoom into the edge. Or in the classes that have 0 modes, you zoom into the origin, you will get different statistics. That is because your orthogonal polynomials like Hermite or Laguerre, they will have different limiting behaviors. So if you know your orthogonal polynomials in the region where they have zeros, they typically are oscillating, so they give sine and cosine. The region where the zeros stop, this is where you get Airy statistics, and Laguerre also have a Bessel limit. So for these 3 plus 4, we have these extra classes. For the classical ensembles, you have only bulk and edge. Now, what is important is that for every beta, we get a different limiting kernel. So we have, for every beta, a different edge statistics, bulk statistics, and origin statistics. And all these limiting kernels are known, of course. I will show some pictures on the next slide. I just would like to mention that rather than looking at density, 2-point density, or so on, we can also look at the spacing distribution. So suppose you order your eigenvalues starting from lambda 0 to lambda n. And then you can ask, what is the probability to have a spacing of distance s between two consecutive eigenvalues? And there's a very simple tool that people have looked at, which is called after Wigner, that will come in a minute. But before we do that, let us look at the local statistics here for Hermitian random matrices. So I will look at the origin and the edge. So let's zoom in here or here. So how does that look like? So this is the yellow curve here that is wiggling is the Bessel density, and the wiggling curve here is the Airy density. Okay. Now, whenever you see a local maximum, that's where approximately the eigenvalues are located. Okay. And so the curve that is here shown, that would be the distribution of the first eigenvalue. You can ask what's the distribution of the second and so on. And that's all known analytically. The distribution of the largest eigenvalue is also famous. This is called Tracy-Widom distribution that appears also in non-equilibrium statistical mechanics problems. This is all nice. And furthermore, we know that these limiting kernels that I don't give you, I just give you the words, Bessel, Airy, they are universal if you study non-Gaussian random matrices. Now in the bulk, the corresponding density would be just the sign kernel, so it would be constant, the one-point function. And this is a third universality class. Now I mentioned that instead of looking at densities or individual eigenvalues, you can also look at spacings. So you can look at what is the probability to find two consecutive eigenvalues at a spacing S. This is what was proposed by
Gernot?
Yes.
Gernot, may I also make a comment? Perhaps you would like to mention also that the scaling is different. In the bulk, level spacing is about 1 over n, and the edge is much larger.
Yes, sure. Thank you, Joshua, for pointing this out. I didn't want to go into these details, but this is of course true. So the scaling with n close to the edge, so this edge of the semicircle typically goes with third power of n, and the scaling either at the origin or on the bulk. So the way you zoom in with n depends on the location. Thank you. Okay, so this is the spacing distribution according to Wigner. So Wigner made a back of an envelope calculation for 2x2 matrices and got out this formula here. So s to the beta e to the minus s square, and beta can be 1, 2, or 3. So these are the three curves here. And miraculously, they approximate the large n limit, the infinite n limit, which is universal, extremely well. So if I would plot here the exact answers, which are known, a bit complicated, you would barely see the difference by eye. Now there's a third curve here, which is a Poisson distribution in 1D, and that is expected to be valid when you have uncorrelated eigenvalues. And here are two pictures about experiments. This is a famous paper by Bohigas, Giannoni, Schmidt. So they show that both the spacings in nuclear data, so scattering of neutrons on heavy nuclei, give spacing distribution that is agreeing with the GOE. So that's the curve that vanishes linearly here. And the same is true for quantum billiards. And I could show you more pictures. Some of them were made here by experimentalists in Bielefeld a long time ago. Take an integrable quantum system like the hydrogen atom and start perturbing it. So the hydrogen atom close to the ionization energy will be close to Poisson. And if you turn on a magnetic field, you will see a transition from Poisson to random matrix statistics. This is well known and studied. I just would like to motivate that we may be interested in curves in between. So we may actually look at this parameter beta here as an interpolation parameter.
Excuse me, when you say neutron scattering off what?
You scatter neutrons on heavy nuclei and you look where are the resonances, and then random matrix theory tells you what the distribution, so a statistical measure of the distribution of spacings in this scattering. You have to be careful that they are in the same symmetry class. You can also look at the distribution of widths. This is really what people have done in the 80s, I would say, and before.
And there's no randomness in heavy nuclei, and there's no randomness in neutron scattering.
Well, a heavy nucleus contains many protons and neutrons, and this suggests, and this was suggested by Wigner in the 50s, that these neutrons and protons behave like a chaotical system. That's why they introduced random matrix theory.
Oh, I see. Well, this picture would suggest that that is the case.
Yes, indeed.
I see.
And this came only, I don't know if I put the year here, this was not possible at the time of Wigner and Dyson. So people had to accumulate a lot more data. You see, these are about 2,000 spacings to see some decent statistics. So only in the 80s, people knew that these suggestions were apparently true.
And I'm sorry to ask another question, but
Oh, go ahead.
what size of nucleus does this first show?
I think people used, well, you know, in the 50s and 60s, people were interested in uranium and other heavy nuclei. And I don't know if people have done this for smaller nuclei, but yes, so the answer is I don't know if people have looked at such a threshold.
There must be a transition somewhere.
Yes.
Okay, thank you.
You're welcome. Okay, so.
Can I just make a comment? Actually, Dyson was able to use some of these distributions to predict that some of the energy levels, when they were tabulated, some energy levels were actually missing, and was able to predict just because there appeared to be holes in the data, that there had to be more states that hadn't yet been observed in uranium nuclei.
Thank you. Yes, and people have also studied from the mathematical side what happens when you start thinning. So you take out levels because you miss them because the resonance was so weak. So this is also an interesting development, I would say, recently in mathematics. Okay, so this is about the spacing in the bulk. Now you could say, maybe in academic questions, so, okay, we know there's Bessel area and sign laws. What about the spacing here, close to the origin? So what about the spacing between the first and second, or second and third? Or here, between the largest and second largest? There must be also spacing distribution. So how does it look like? So that's what we calculated with Valentin and Mario, and we found, at least at the origin, we can calculate these, yes. And they look almost the same as in the bulk. So even though we know the statistics is described by completely different kernels, the spacing distribution is really blind to that. So here are some data. Again, I'm not on my tablet and can just zoom by, you know, making this movement by my fingers. So, but you can see, I mean, the curves are very close. So k = 1 is with the largest deviation. So spacing between first and second. And here we show the distance. And you also see that the black curve here, that's the Wigner-Surmans. It's not an exact answer, although some people confuse it. So there's also some difference between the Surmans and the true spacing in the bulk. And you see that very quickly for distance between third and fourth, we are in the same realm. So the spacing does not detect that we are at a different symmetry class here. So what about the edge? So the spacing between Tracy-Widom, the largest eigenvalue, and the second largest. Now here we don't have analytic results, so we just do numerics. And I mean, if you see from here, I mean, how can you detect this from data? I mean, this is next to impossible. So again, at the soft edge, the spacing is basically the same as in the bulk. It will not be the same mathematically, but it's very close. So what I'm saying here is that the spacing is not a good measure to distinct different universality classes like Bessel, Airy, or sign. Okay, so this was the first result I mentioned in the introduction. So let's go now to non-Hermitian ensembles that are probably closer to the heart of many of you. So what do we know about the spectral statistics in the large and limit? Again, I will just give some results in a nutshell. So remember, there are many classes. Now it turns out that the global density is just what is called the circular law. So the density is just constant on a disk and then goes to 0. And if you go back here, this is not difficult to see. You see, I gave the kernel here. So just plug in here Z and Z. So this is e to the minus Z modulo square. This is an exponential function, e to the plus Z modulo square. So this gives a constant, 1 over pi. Now this is only true when Z is larger, is smaller than square root of n. Otherwise, this will not compensate this, it will go to 0. But this is roughly how you can see that. And this was first introduced by Gernot. Now, for the 3 Ginevra and 3 chiral one, we know that this circular law is true. And for the other ensembles, there's at least some numerical evidence. So once again, the global statistics looks almost all the same. And now you will ask, okay, do we have 3 different classes, origin, bulk, edge? Now in the Ginevra ensembles, the origin, the blue point here is not special because it doesn't have 0 modes, but otherwise other ensembles do. So I will come to that. Now, there's one more point about local statistics here. So you have perhaps noticed, perhaps not, in the joint density that I gave here. Let me point on that. So this joint density, it's not a Vandermonde, but it contains a term z minus z star at the same value. So the probability to have 2 real eigenvalues is 0. Okay, so that's why if you zoom in at the, if this is a circle of radius 1 at the order of 1 over a square root of n here, you will find that for the symplectic ensemble, there's actually a little gap here. And likewise, for the real ensemble, I already mentioned there are real eigenvalues actually of the order of square root of n. There will be a density of real eigenvalues that is actually constant here. That's the green bar. So in the complex plane close to the real axis, all these 3 Ginevra ensembles are different. And we understand all their kernels. The same is true for the chiral ones. So we know all the kernels, all the limits, and they are all different. So that's along the real line. Now you may ask, aha, but what if I am in the bulk here, or if I look at the edge statistics? Is it still true, like for the Hermitian ensembles, that all give different results depending on beta? The answer is no. In the bulk and at the edge, away from the real line, there's only one symmetry class that is the claim at the moment for the Ginevra and chiral one. We know that, we can prove that. And the symmetry class is the one of the complex Ginevra, so Ginevra unitary ensemble. So the random matrices that were much more complicated and had a Pfaffian structure, all will simplify to become determinantal when it goes to the bulk and to the edge. Now I could explain heuristically, maybe going back again some slides. So if you look at this symplectic ensemble here. Now, if you are away from the real line, you don't care when you look at local statistics what your complex eigenvalue, your complex conjugated eigenvalue does. So this term here will not matter. And also this, the repulsion from the real axis, will not matter. So all that will matter is this one, and that's exactly the same as for the complex ensemble. So this is heuristics. Of course, you have to do that rigorously on the level of point processes, and this can be done. Now, for all the other 32, we don't know, because we don't know the joint density. So you can still ask the question, is there some other universality class out there? And one tool that we have used and others have used and suggested is to look at the spacing distributions in the complex plane in radial distance. So what do I mean by that? So let's say the red crosses are complex eigenvalues. And if I take this one here in the middle, its nearest neighbor is the one just above, and the distance in radial distance is this black line here. So that's our S. So I will now look at the spacing distributions in the complex plane, and I will look at the bulk, because that's where we have one symmetry class. Okay. So because this is the symmetry class of the Ginevra unitary ensemble, let's look at this. This is known explicitly. I will not give you the formula. It is a sum over powers that contains incomplete gamma functions. So there's no worry to write this down for any n. Now there's one difference between Hermitian and non-Hermitian. As I showed you, or at least I argued, for Hermitian, Wigner's calculation for 2 by 2 matrices was good enough, surprisingly. Now here in the complex plane, it's not. So the blue curve here is the limiting spacing distribution in radial distance. And these are the spacings for n equals 2, 4, 6, up to 20. So they converge rapidly, but 2 by 2 is not good enough. So let's use the one for 20 or larger. I mean, then you cannot see the difference. I have plotted a second curve here, the orange curve. Now this is the Poisson distribution in 2 dimensions. So throw points on a disk at random, no correlation. The radial measure will give you a linear repulsion, even though they are uncorrelated. So this is the curve that I will show you in a moment. This is Poisson. So, and again, people would like to know, perhaps it's also true in the complex plane that chaotic quantum systems follow random matrix statistics, and integrable systems follow Poisson. And so for that, you would need an interpolation, but before I show you a plot, so this is again the Geneva spacing distribution and numerical simulations of real complex or quaternion matrices. So also numerically we see they are all the same. So this is now numerically generated curves because we only know Poisson, and in fact beta equals 2 here analytically. So generate complex eigenvalues that are subject to logarithmic interaction. So we now take Vandermonde modulus to the beta, and then determine the spacing distribution for different values of beta in the complex plane. So you see that there's some curves. This is here beta equals 4. This is beta equals 0, so Poisson. Now let me show you a picture from a paper with Thomas Prosen and also Adam and Mario. So here, what is plotted here? So it is plotted the spacing distribution, not of the Hamiltonian, but of the Lindblad operator for various degrees of integrability. So Thomas is a great expert in these spin chains, and he knows what kind of boundary conditions you can pose that it's still integrable, and when do you start destroying the integrability. So here you see this is the integrable, most integrable case that follows Poisson in 2D, and then we crank up integrability, well, unintegrability, non-integrability, and then you start seeing, okay, this is beta equals 2, and this is now Geneva. So this gives some evidence that also here in the complex plane, we have some transition from integrable to non-integrable. This is maybe as an aside, but it's a good motivation to ask, can we do something like the Wigner surmise in the complex plane? Okay. Now, this is something what we tried. So what can we do? We can do 2 by 2 calculations. So now suppose I have a complex beta ensemble. So I take a Vandermonde modulus to the beta, and I take a Gaussian measure for the complex eigenvalues. In this setup, Patricia calculated the spacing distribution for 2 by 2 exactly, and this is the answer. So now it reduces to Geneva when beta is 2, so then this becomes cubic. This is also collected down here. And sorry, there's a square missing here. So this should be s to the power 2. And this also reduces to Poisson when beta is sent to 0. This is in stark contrast to the Wigner surmise. The Wigner surmise works, the better, the more you increase beta. This one here works better when you decrease beta, so close to Poisson. Now, we know that for Geneva, 2 by 2 results are not useful. They're quite far from the infinite and limit. So we will come to that on the next slide. But here are 2 other examples. So here are 2 classes out of this 32 that are unknown. And these are complex symmetric matrices. According to this Cartan classification, they are called A1 dagger. And complex quaternion self-dual matrices, they are called A2 dagger. Never mind. Also in these 2 classes, the spacing can be computed for 2 by 2. And it looks quite similar to the Geneva case, but hey, here's a McDonald function. So this has a logarithmic singularity. And the reason these were studied was because these symmetry classes appeared in kicked rotors or in other physics systems. So they are not in the Geneva universality class. So what is the spacing for this Geneva beta? What is the spacing for these symmetry classes? At least numerically, we can assess that because we don't know an analytic result for large N for these symmetry classes, but you can do simulations. But before I come to that, let me show you another idea here. So I said also that the 2x2 result we have for beta ensembles are not useful in the large N limit. So we had the idea that we will use beta as a fitting parameter. So we want to get a semi, or let's say an approximate analytic description for this spacing in beta ensembles for which we have only numerics. So let's simulate some beta, let's say beta equals 1, or I think this is 0.6. These are the histograms. The orange curve is the 2x2, doesn't fit. And then if we use beta as a fit parameter, we get quite a good, well, approximate analytic result. And the fit is just the polynomial in beta. So we do that once for our test cases. It's basically a linear fit. So beta effective is just some constant times the real beta. So in this case, we do have some approximate description. It's not as good as the Wigner-Sommers. This is the work with Patricia and Adam. But if you have data, you can use that as a first guess, and you want to check interpolating between Poisson and some other beta. Okay, so let's now come back to these two symmetry classes here. Now, there was a striking result by the Japanese group in a paper by Hamasaki, Ueda et al., where they showed, they claim numerically that these are the only two classes out of all 38 that have a different spacing distribution from the Geneva ensemble. So they claim there are 3 classes in the bulk out there. And so these are the orange histograms here. So these are complex symmetric quaternion self-dual. Now, what did we do? We compared, first of all, the red curve, that is the analytic results for these 2 symmetry classes here. Well, because there's no surmise, this will not work. And then we said, aha, let's try to fit the spacing of these 2 different symmetry classes by a beta ensemble. And it turns out that I would say the blue curve is a very good approximation to the spacing in this class A1 dagger at non-rational beta. So the Geneva one would have a maximum here. I did not plot in another curve because then it gets messy. And this is the symmetry class A2 dagger of complex quaternion ones that is fitted by beta 2.6. This is puzzling, but I think it asks for a deeper understanding. And I think this is where we are at the moment. So let me summarize. I don't have a written summary on these slides because, but I can tell you what is the summary I would like to present. So first thing is the universality classes of real eigenvalue statistics of Hermitian random matrices is very well understood. So I've shown to you that there are 10 symmetry classes, and depending on the large N limit, in the bulk, for example, there are only 3 different symmetry classes. There's 3 different universality classes that depend on beta. Likewise, at the edge and at the origin, you can really distinguish between the Broglie-Lyubov-Tijen, these particle hole ensembles, and the other ones. Now, for complex eigenvalues, I think we are just at the beginning. So we have 6 classes where we understand everything because we have a joint density, we have a kernel, we can take limits. Also there we understand analytically why they all reduce to a determinantal process in the bulk and at the edge. I think it will be difficult to derive these joint densities for the other classes. So maybe other methods will be called in for example, supersymmetry, replicas, or just doing probabilistic tools, just studying non-Hermitian matrices with IID random variables and see what can be said about local statistics, and this has started. I would like to finish with a warning, however. We learned from the spacing distribution of real eigenvalues that this is not a good measure to distinguish different universality classes. We saw that at the origin, in the bulk, and at the edge, we get the same spacing practically. There are very small deviations, but for data, this is very difficult to see. However, we know that the spectral statistics is very different in these different sectors. Now, in the complex plane, the claim is that, well, at least numerically, we see that all 32 classes show only 3 different spacings. So I think it will be, we will have to find out, maybe this is not a good measure to say that there are only 3 symmetry classes. Okay, with this, I would like to close and thank you for your attention.
Thank you very much, Gernot.
Thank you very much.
Was there any text on the last slide other than
Yes,
the title?
there was.
That's the only bit we missed now.
Yes, because I prepared the other slides where there was text everywhere and you couldn't see any of them, but that's why I showed you the previous version where I had stopped sharing. I stopped yesterday night. Sorry about that.
It was all fine except the last slide.
Yes.
Thank you, Gernot. Questions, comments?
I think there's one hand.
I think this is
Philip.
Philip, go ahead.
Thank you. First of all, again, thank you very much for this presentation. I have a question and a comment. Okay, the question first. Going back to this whole notion that a heavy nucleus is a random system, I've heard many talks on heavy ion collisions, those that are looking for the quark gluon plasma, for instance. And at least I've never heard any discussion of random matrices. Do you know whether this is known to that community, or maybe it's not relevant?
Yes, definitely.
Because the energies are so high.
Well, I think it is known, but it's a different. If it's a different story. I mean, you have a different experimental setup, of course. So when you try to create a quark gluon plasma, you basically smash nuclei, hopefully quite centrally, and then you create this plasma, and then there are much more rough data that you can extract, like temperature, pressure, when you have freeze out and so on. So these are bona fide statistical mechanics quantities, but you are nowhere near to see, what is the spectrum. So also I wouldn't know, if you have this this glue ball, what could you look at? I mean, people have looked, of course, also at these vibration modes of heavy nuclei. I don't know if any random matrix statistics has been done here, but I think it's really very different.
Gernot, there was by Misha Stefanov, actually one of the first papers to double the matrices in the mid-90s by Misha Stefanov.
Yes. But
including chemical potential, which renders the Dirac operator known.
Yes, but this is not about the quark gluon plasma. I mean, this is more
more about the field structure. Yeah.
In some sense, it is, but this is really then you are leaving where you can say something about the spectrum. You can just say, I mean, his paper was basically to understand why is the sequential approximation and lattice gauge theory giving the wrong answer. And he succeeded. That was one of the reasons and motivations to create these chiral non-Hermitian ensembles, because then we could study Dirac operator eigenvalues for their complex eigenvalues. But this is really very far below the phase transition. So
that's true.
Okay, well, thank you for that. And now the comment.
Please.
Ordinarily in quantum mechanics, I introduce a path integral, where the action itself is the Legendre transform of the Hamiltonian. But each path has a definite weight, so that it's not random. But suppose I just took the path integral and I put different weights on the different paths. Would that be what you're doing?
Well, I mean, as far as I understand path integrals, you have to really integrate over all possible weights, and then you get the right answer. Now, there is an analogy here in some sense. So the path integral formulation will be when you, let me try to get to this. So when you have the, when you have the Hermitian random matrices. So let's look at this one here. Okay, so now you put your Vandermonde in the exponent, and then you have a kind of statistical mechanics problem. Now, if you then replace all your sums by integrals, and you want to know what is the free energy minimizing this setup, that's what you will get in the path integral formulation. So in mathematics, this is called equilibrium measure. So that's the density that will then minimize this function, and the free energy can be then expressed in terms of this density. And I think that is the leading order result, and that you can also do using a field theoretical approach.
Okay. Anyway, what I was thinking was, you have a complete basis of paths,
Yes.
but they're all given equal weight. What I'm asking is, what happens if we didn't give them equal weight? It would seem that we have to come into one of your situations.
Well,
that's all I would.
Yeah, I understand. Thank you very much. I mean,
I haven't done a calculation.
Yes, but I think, especially in the comparison with field theory that I did not dwell upon at all, although this has been in my interest for a long time in the past. I think the people in the lattice gauge theory community who were first surprised that random matrices do describe small eigenvalues of Dirac operators that they study on the lattice, they were a bit confused by, we have this randomness here. But I think we now understand what is the approximation in which lattice gauge theory is described by a random matrix model. And the approximation is, you have to go, you have to look at chiral symmetry breaking, you have to go to the low energy theory, that's a theory of pions. And this is like going to a sigma model here in the random matrix language. So, and then if you like there's nothing that is random in that sense. So the approximation you make to describe field theory, I think is clear and less confusing now than it was in the beginning.
Okay, thank you. Thank you.
You're welcome.
I have a question. What was exactly wrong with the Bernard-Leclerc paper? I mean, they just use some symmetries to do the classifications. Did they not notice that some are identical, or what was the correction?
Yes. I think that was they did not identify some classes, so they overlooked that classes that should be counted as the same, they counted as different. So I think the modification that has to be done according to the suggestion where this was first pointed out in this paper by Kawabata, Ueda, and other authors, was then picked up again by Bernard Leclerc. So they say you can actually amend, and if you correct their mistakes in the archive version 1, which is I think from 2000 or so.
It's 20 years old. Yeah.
Yeah. So the classification is now correct.
Okay, it's muted. Continue. There was
somebody.
Yeah, somebody unmuted himself. Okay. Go ahead.
Yep.
Keep going, Gernot.
Yeah. I think I answered your question. I hope. I mean,
maybe I missed some, or maybe some addition. Yeah. So did they actually miss out some symmetries? Can you still use the same set of symmetry operators for the classification, or is there something deeper mathematical behind?
No, I think
Well, it was just an overlook.
I think it was just an overlook and
Okay,
miscounting. So the set of operators is exactly the one, and I think also the Japanese group acknowledges this, and so they have rephrased this classification, and I think it was good that this was picked up again, because I think now, also given that Bernard and Leclerc reacted and corrected, we can be hopefully sure now that this is all that it is.
Nothing deep. Okay, thank you.
Not 42 as readers of the Hitchhiker's Guide to the Galaxy would have liked to, but yeah.
So novels have to be rewritten now.
Well, we have to seek for another question. Yes.
Any more comments, questions?
Yeah, may I?
Sure.
Yeah, so first of all, Gernot, thank you very much for this excellent talk. Gives a clear picture. And I agree completely that you need to do these empirical experiments in order to get information to know where to continue with more heavier weapons. So what I wanted to ask, first of all, do you understand do you have a deeper understanding why the surmise, Wigner surmise works really well for the Hermitian cases, whereas, as you mentioned, in the non-Hermitian cases, such an ansatz pool is really
no, I'm afraid I don't, but I think I understand now why the spacing at the edge and in the bulk is the same, because if you have 2 by 2 matrices, the edge and the bulk is the same basically. So, but I don't understand why Wigner's calculation is so precise. And
so could it be because of quantum mechanics? I mean, if you really think in terms of second order perturbation theory in quantum mechanics, in Hermitian quantum mechanics. So when you have 2 very close levels, I mean, the spacing of these levels is really much smaller than all the other levels in your system. And you know that levels repel. And you know also that all your eigenvalues are on the real axis because it's Hermitian. So then more or less you can ignore all the other levels to a good approximation. But if you're in the plane, if your Hamiltonian is non-Hermitian and you have points in the plane, so the entropy, I mean the number of points, can somehow offset the large denominator which comes from second order perturbation theory, and maybe this is what getting everything out of control. So
well,
maybe
I very much like your explanation for the Hermitian case, but I'm not sure about the.
It's not mine. It's Wigner's.
Yeah, sure, and I think Kutzhake also explains this very nicely, but in his book. But I think okay, we have studied one other limit quite recently, and that's the limit when beta goes to 0. Namely, when beta goes to 0 at a rate like 1/n. And when I say we, I mean Sung-Soo Byun from Korea, who's now a postdoc. So we did this for the non-Hermitian case. And previously, this was done by Alice Guionet and Jean-Philippe Bouchot and Romain Alès for the Hermitian case. And in that limit, when beta goes to 0, like 1/n, in this free energy, like what I was trying to answer to the previous question. So you put all your Vandermonde and stuff in the exponent, and replace this by integrals. For fixed beta, you will only need the contribution from the energy. But when beta goes to 0, the entropy contribution will actually count and make a difference. So, so in that limit, I know that it does contribute. For fixed beta, I don't know. I mean, it is subleading, but maybe in local statistics, it will play a role. I don't know.
Well, I think it's worth thinking about it because it's the only obvious difference between the two cases. Okay, thank you. Another question, where do you put normal matrices in all this story?
Well, I would say I would put them in the, okay, let's start with a complex one. So the magic here for the for the Ginevra ensemble is that you have this upper triangular matrix, but because you have a Gaussian, this decouples, so you can integrate it out.
Yes.
So that means you get the same as if you had started with a normal matrix where this T is absent.
Mhm.
Now, if you look at different distributions, like, for example, fixed trace, or you add higher order terms, it's not so obvious. But I would think that typically, at least in the case of Gaussian matrices, they should be in the same universality class as the Ginevra ensembles.
But for example, if you look at the real Ginevra versus real normal matrices,
Okay.
which are not Hermitian, then it's not the case, because you don't
I
have
see.
these. It's diagonalizable. It's like
Yes.
it's like the full. Well, it's like the last, the higher sector of the real Ginevra with maximal number of
Okay, and
eigenvalues.
that's of course then GOE. Yes, that's right. So, but I think for I don't think this has been looked at so much, but I think for complex, I would say they.
I know that for the complex normal non-Hermitian normal matrices, you get the van der Waals squared.
Yes.
I know that. Yeah.
And for the symplectic ones, I think there is more of a debate. Of course, you can formally replace this Gaussian here by some potential, and then just define an eigenvalue model. But then you have to check, is this really representable as a normal, let's say, quaternion matrix ensemble? So this I don't know.
Okay.
Because from normal, you would expect perhaps that this does behave like 1 number to the power 4.
Yes.
But I mean, there's an ensemble known, actually, this antisymmetric, this complex Hermitian. There's a paper by Matthew Hastings. I don't know if you know that one, where he argues that it's from 2000, that at least approximately at large distance, it behaves like 1 number to the power 4. But also there, we have no solution analytically, and this is only an approximate answer.
Okay.
So I think it's open.
Okay, thank you.
Thank you.
More questions, comments? If not, then let's thank Gernot again for this very nice talk. Thank you, Gernot.
My pleasure. Thank you for all the
Very
questions.
You.
Thanks a lot.
Thanks.
May I still ask a question?
Sure.
Go ahead.
Uwe.
Yeah. I forgot. It's just for curiosity. There have been a lot of information for differential operators in the complex plane, and there you have the eigenvalues which are located on certain graphs. This happens. There are very nice papers, for instance, from Boris Shapiro and so on, and they found these complex eigenvalues are located on graphs. Do you know about some kind of matrix model approximation of these pictures, just to build up some equivalence? Could it be that one can model these setups also in terms of your random matrix models? Do you know about something like this?
No, I mean, I know about people studying random graphs and real eigenvalues, like Jens Bolde, for example, in Royal Holloway, also, and maybe other people in the UK. But Sven Gutzmann also in Nottingham. But I'm not so familiar with these random graphs. But it's very interesting. So is this Boris Shapiro or?
It's Boris Shapiro from Stockholm, for instance.
Okay, okay. Then I will have a look. That makes sense. So.
Okay. Then was just wondering. Okay, thank you.
Sure. Thank you.
Okay, thanks again, Gernot.
So is it also so warm in London, or?